Welcome to clickmyproject.com. Now we discuss about the product for efficient register renaming and recovery for high performance processor. Then we discuss about the abstract for the product. Modern superscalar microprocessor implement the out of order and super spacey execution to increase the performance. Many mechanisms are devised aimed at enhancing the amount of instruction executing concurrently. These mechanisms requires the register renaming technique to solve the write after the read and write after the write data hazards. Register renaming distinguishes two kinds of registers: logical and physical register. Logical register are those are used by this compiler, whereas physical register are those actually implemented in machines. Typically, the number of physical register is quite larger than the number of logical register. When the instruction that produce the result is decoded, the register renaming allocates a free physical register. The logical destination register is said to be mapped to the physical register. Modern superscalar processor implement the register renaming using either random access memory or content addressable memory tables. The design of these structures should address both access time and misperception recovery penalty. Although direct mapped RAM provide the faster access time, CAM are mostly appropriate to avoid recovery penalties. The presence of associative pods in CAM, however, prevents them from scaling with the number of physical register and pipelined with negatively impacting performance, area and energy consumption at the rename stage. In this paper, we present a new hybrid RAM-CAM register renaming scheme, which combines the best of both approaches. In a steady state, RAM provides a fast and energy efficient access to register mapping on MIS mechanism. A low complexity CAM enabled to immediate recovery. Experimental results show that the four-way state-of-art superscalar processor, the new approach provides almost same performance as the ideal CAM-based register renaming scheme. The flow diagram for the product. First of all, the input binary bits are applied to the CAM architecture. The CAM architecture to consider the number of content and the content to calculate the number of ones in the address allocations. Then the number of ones to be calculate the add or even parity. Then the add or even parity process to apply the search data for parity content. Then compare to the parity content of the input address allocations. Then calculate the matcher line selection. The matcher line selection is no two conditions wise satisfied. The yes conditions to be go to the next processing and the no condition to search data for parity content. This process is to be continuously and search the content. If the line is matcher line process, then go to the select the content for the CAM data, then apply to the RAM process. The RAM process is the one of the memory oriented process. Thus the RAM process to get the output data and read and write, then satisfy the read and write architecture logic. Finally, we see the output for the product. First, we open the CAM's architecture for Xilinx ISC project. Our project was developed in VHDL language and used the structural modeling process. Then select the RAM-CAM process to select the simulation process and to double-click the simulate behavior modeling process. This process is to compile our program process. Then compile is successful. Then open the Xilinx ISM project. This block is used to simulate the project. Then apply the clocking process. Then apply any of the address locations. Then activate the writing conditions. Then the data is then to activate the clock signal. Then to play the clock signal and to deactivate the reset function. Then to write the data and to read the data. So the clock signal to be activated and the read the data to be activated. Finally, the RAM process is to get the content and to read and write the RAM data output data. Then close the simulation result and to select the implementation. Then to create the view RTL schematic diagram. Then add to create the schematic diagram. This diagram to represent the CAM and RAM block, how to combine our the CAM block and RAM block. The content to create search the CAM block and get the content to apply the RAM block. Then the RAM block read and writing the process. One of the slave process to create the CAM block and the master process to create the RAM block. This RTL diagram to represent the how to logical block placed in our architecture design. The technological diagram to place the what are the lookup table, flip-flop and input output process to be placed by the technological diagrammatic representation. Then go to the design summary process. The design summary process to set the synthesis report. This report to present the what are the parameters to process in our CAM RAM architecture. The lookup device utilization process to display the how many lookup tables and slices register, then input output pairs to be placed in our CAM RAM block architecture design. Then the timing summary results, what are the time for our process running for the CAM RAM architecture. Then the speed allocation for maximum frequency to 749.232 MHz in our CAM RAM architecture. Then the latency level for the outer and before clock in RAM CAM architecture designs.